part 2 of week 3 homework solutions. Now I am talking about rules of inference and determining if arguments are valid. So this first example, introduction here to rules of inference, we're just taking a statement about Jerry. He's a mathematics major and a computer science major, trying to conclude that Jerry is a mathematics major. So I think probably this makes sense, but I'm going to write it all out symbolically and write out the corresponding implication, prove that it's a tautology so that you can really see what I mean by a valid argument. So if I write this out symbolically, Jerry is a mathematics major is represented by our proposition P. Jerry is a computer science major is represented by our proposition Q. And we're saying therefore P. So this corresponding implication is I take my premises, I've only got one premise now, but if I had another one I'd join it by and then my conclusion and show that it's a tautology. So I could do this with a truth table. I'm going to try to do this with just logical equivalences. So I'm going to work with my left hand side here. I'm going to change my implication to the negation of the hypothesis or the conclusion. If I negate an and, it becomes an or, and then I negate both pieces. Then I use the commutative property of or, and then the associative property of or to join the p's together. And then I get P, not P or P is true, or not Q. True or anything is just true. So I've shown that this is a tautology. And this makes sense if we think about the AND operator. The only time an AND operator is true is if both pieces are true. So in an argument, we're given true premises, and then we try to draw some conclusion from it. So the only time an argument is valid is if premises imply conclusion is always true. And so we've proved that. So it is valid, and this is our justification, this proof that this implication is a tautology. Alright, so this is really similar. We've got a little bit more complicated statement here, but we've got George does not have 8 legs, so that would be the negation of the proposition P. Implies George is not a spider, so that'd be the negation of the proposition Q. So that's one premise. Another premise is that Q is true. And then from these two premises we conclude that P is true. George has 8 legs. So the corresponding conditional statement would be our premises joined by and showing that that implies the conclusion is a tautology. So if this is a valid argument, then I know that this corresponding implication is a tautology. And I believe this is actually one of the rules of inference listed on the table, so you could reference that rule of inference here, but I'm just going to go ahead and prove that this is a tautology. So I'm going to rewrite this implication in the negation of the hypothesis or the conclusion. So that would be the negation of P is P, or conclusion is not Q, and Q. And that implies P. Distribute that Q, so I'll have P and Q, or not Q and Q. Not Q and Q is going to be false, so I'll have P and Q, or false implies P. Anything or false is just the original statement, so P and Q implies P. Negation of the hypothesis or conclusion, that logical equivalence, I can rewrite this implication. And I like that because I know then I'll get a negation of P and an or, and I'll be able to move these around in any order that I want. And keep in mind, you can always do a truth table on these, but for me it's just easier to just go through and do these steps. And so we get that this is true, so it's a tautology. So because this implication is always true, I know this is a valid argument. So valid argument, and your justification here can either be the series of logical equivalence proofs or a truth table or referencing the corresponding rules of inference. Now we're given some premises and conclusion and trying to determine if it's a valid argument. So Randy works hard, so our premise is W. If Randy works hard, then he is a dull boy, so D. And another premise is if Randy is a dull boy, then he will not get the job, so negation of J. And we want to show that this implies that Randy will not get the job. And so we can kind of see how this would flow, and we could actually attach several rules of inference to get to this conclusion here. So we could say, let's see, for step 1, we could say W implies D, therefore D must be true if W is true. Now we'll have D is true. D implies not J is true, therefore not J is true. Okay, so we could do it that way, breaking it up. Or we could just join it all together. We could say W and W implies D and D implies J, not J, negation of J. All this implies negation of J is a tautology. So this is kind of a big one, but I'm going to go through it just for you to see more examples of this. Let me go ahead and rewrite these implications. Negation of W or D and negation of D or not J. All of that implies negation of J. Let's go ahead and apply or distribute that W and. So I'll have W and not W, or W and D, and not D or not J. Implies not J. So W and not W is going to be false, or W and D and not D or not J. So false or something is just that something. So I'll have W and D and not D or not J. So now using the associative property, I can group that D with the not D. So I'll have W and D and, so I'm going to group this D because I want to put it by the not D. So if I use distribution, I've got D and not D, or D and not J. So I'm going to have D and not D is false. So I'm just going to end up with W and D and not J. Implies not J. So this is looking good because I know that I can rewrite this implication as the negation of the hypothesis or the conclusion. So that will get me to all ors in the hypothesis. So I'm going to have negation of this hypothesis So I worked through this proof that this argument is valid by showing that the corresponding conditional statement is a tautology. I'm going to post these notes online, so I won't do it in this video. Just look over my steps and see if you can follow my work to show that the corresponding conditional is a tautology for this argument here. Now we've got some quantifiers and we're trying to find out some conclusions from the given premises. So let's just go ahead and introduce some predicates because I know that I have quantifiers, so I want to use predicates and not propositions. And then I'll see if I can get these conclusions. So I'm going to say our domain of X domain is all animals, and let's say I of X is an insect. So I'm just looking through my different statements and trying to determine how I would interpret these statements symbolically. So 6 legs, 6 of X, X has 6 legs. And let's see. So if I write out the first two statements for all animals, if insect, then 6 legs. So it doesn't say anything about 6 legs, but it does say that if you're an insect, you have 6 legs. Think about the logically equivalent contrapositive would be not 6 legs and not insect. So our next statement is dragonflies are insects, so I of dragonfly is true. We also know that spiders do not have 6 legs, so the negation of S of spiders is true. And spiders eat dragonflies. I'm just going to leave that one out of there for now, because I know that doesn't imply dragonflies eat spiders. That doesn't make sense. So let's just try to work with these 3 statements here. So this is saying for any animal that I choose, if insect, then 6 legs. Here I'm saying I is a dragonfly. So this tells me that S of dragonfly must be true. So if I write this out, for all X, I of X implies S of X. I know that I of dragonfly is true. So then that must mean that I can conclude that S of dragonfly is true. So this tells me that dragonflies have 6 legs. Now, I know something about the negation of X. So I know that I of X implies S of X is logically equivalent to the negation of S of X implies negation of I of X, just using the contraposition there, contrapositive. So I can also write this as for all X, if the negation of S of X is true, then the negation of I of X is true. So I know that spiders do not have 6 legs. So then I can conclude that a spider is not an insect. That's really all I can conclude here. Spiders are not insects. Okay. Okay, let's go ahead and write this out symbolically to better understand these premises. So I'm going to say D is I am dreaming. I'm going to say H is I am hallucinating. And E is I see elephants running down the road. Down the road. Okay, so let's write out what I've got here. So I am either dreaming or hallucinating. So I'm going to say D exclusive or H. I am not dreaming. So negation of D. If I am hallucinating, then I see elephants. So let's see. Let's think about what we can conclude with D exclusive or H, not D. So if any or is true, at least one of them has to be true. So I'm able to conclude that H, I am hallucinating, must be true. Because I know that these three statements have to be true. So if D is false, to make this one true, H has to be true. So I know that I can conclude I am hallucinating. So I know that H implies E, so I can conclude E. I see elephants running down the road. And if I am hallucinating, I know I can't conclude this. And I already am seeing elephants, so I can't conclude I do not. It is not valid. I'm looking for a case when my premises are true, but my conclusion is false, because that's the only case when my implication would be false. So if it's not valid, true implies false is false. So I want to see if this happens. So I want to find truth values of P and Q that make this happen. So let's just break this down here. I want to see a case where P implies Q is true. I want not P to be true, but I want not Q to be false. If not Q is false, then Q must be true. If not P is true, then P must be true. False, excuse me. So now we're already kind of stuck with truth values of P false and Q true. Let's just make sure that that works here. I've got false implies true is true, so that checks out here. So if P is false and Q is true, P implies Q and not P are true, while not Q is false. These truth values prove this argument is invalid. Let's look at the next one, really similar to this one. I'm trying to figure out if this argument is valid. To start, I'm going to try to prove it's invalid, and if I hit a roadblock, then I'll sort of switch strategies. So if I'm trying to show an argument is invalid, I want to take its premises, figure out if there's a situation where all my premises are true, but my conclusion is false, because then I'll have shown that it's invalid. And if you can't figure this out, then it's possible that the argument is valid, and then you want to prove that this is a tautology. So I want to find a situation where situation with the truth values of P, Q, and R, where P implies R is true, Q implies R is true, negation of P or Q is true, but the negation of R is false. So if I start here, this is the only one involving just one proposition. So if not R is false, then R must be true. Okay, so keep that in mind as we're going up here. So if the negation of P or Q is true, then I know that P or Q is false. Okay, if P or Q is false, the only time an or statement is false is if both truth values are false. Okay. So let's just verify. If I've got P, Q false, R true, let's see, I've got false implies true is true, so that's good. I've got false implies true is true, so that's good. And then false or false is false, negation true. Okay. So this is invalid, and I will just write here if P and Q are false and R is true, P implies R, Q implies R, and negation of P or Q are false. The premises, let me add this in, the premises are true, are true, while the conclusion, not R, is false. This shows the argument is invalid. Alright, let me know if you have any questions on the homework, if you want to talk more, and I will see you soon.